Because so many of you are having a hard time getting Atomsmith to work, I want to do this little demo here. So here's the blog post I wrote, and what I'm going to do is run through the directions that I gave you and show you what's going to happen. So the first thing is put about 16 water molecules in the box, start the simulation, and then vary the temperature. So that's what we're going to do. We're going to go here to Atomsmith and get everything open here on Atomsmith. And I'm going to go and simulation, open the gas lab, and I'm going to come down here and I'm going to put some water molecules in there. And if you get this to work, you can play with it, but put a whole bunch of water molecules in here. Probably not 16 actually here, but then I'm going to simulation and I'm going to start the simulation. And you can see that the temperature here is room temperature, and so you can see the water molecules bounce around here, and you can see them kind of interacting here, and they're going to interact. Now I'm going to slow this down, and when I say slow it down, there's less kinetic energy, and less kinetic energy means that water is going to be colder, and so you can see what happens when you slow it down. These guys have a nice, starting to form a nice crystalline structure. These guys are forming a little crystalline structure. Let's heat it up a little bit to get them to move closer together a little bit more. Hopefully we can get them to bounce around. So right there we got an ice crystal formed, and you can kind of hopefully see a little bit, what's interesting about the ice crystal. It's nicer if you can manipulate this yourself. So if you can get Atomsmith to run, it's fun to play with. So I'm going to start it again here, and then I'm going to heat it up. And so what you ought to get from this is the difference between a liquid, a solid, and a gas. So obviously this is a solid. It's below 273 Kelvin, which is 273 Kelvin is 0 Celsius. And so it's a solid. You heat it up a little bit. Okay, now we're into liquid phase. And hopefully you can see how the molecules are interacting a little bit differently. Okay, so that's what a liquid is. And then if we heat it up a lot, you can see, what a gas is. Okay, and really all it is kinetic energy and the attractive forces of the water molecules. Okay, now the next one. So you should be able to explain how molecular motion differs in solids, liquids, and gases. We just saw it. You should be able to describe it. You should be able to identify the intermolecular forces at work. Okay, so now let's try this again, but let's do methane. And so I'm going to stop this. I'm going to get a box builder. I'm going to clear the box, and then I'm going to put some methane in here. And methane, if you'll notice, has about the same mass as water. But if you look at methane, it's 1 carbon and 4 hydrogens all around it in a tetrahedral formation. So if we start this and see, okay, well, methane should look like a gas right here. If we slow it down, though, what happens to methane? We're below 100 K. We're at about 90 Kelvin here, and hopefully you can see, even at 90 Kelvin, these guys don't seem to like stick together. And we bring it down even lower. Okay, and so we can actually put on these different, like I can show dipole-dipole interactions, and of course there are none. Hydrogen bonds, of course, there are none. And London dispersion forces, well, there are London dispersion forces, and that's basically the only thing holding this together. And of course, methane is a gas down to very, very low temperatures because of this. Okay. Let's see, water, ethane, and ethanol out of the box. I'm going to skip that one, and I'm going to skip these other ones here. And I'm going to do the really cool one, which is if you go and open model file, and I have stearic acid saved on my computer, and if you look at stearic acid, you can notice that it's got a hydrocarbon chain here. It's basically a whole bunch of methane stuck together. And then over here at this end, it has an oxygen, and a carbon. And so this is, this is a, well, it's a carboxylic acid group. So this is a fatty acid molecule. And if we stick a couple things in there, let's stick some water in there. 1, 2, 3, 4 waters. And we stick some hexane in there. Hexane, of course, is just carbons and hydrogens. And then we run the simulation. We can see what happens when we do this. We'll heat it up a little bit to get the molecules moving a little bit. And you should be able to actually predict what's going to happen. Okay, so you can see here, this is stearic acid. Here's its acid group, here are the water molecules, and then here are the hexanes. And if we go ahead and put on the hydrogen bonds, so we can see hydrogen bonds up in here. See the little green dots that show up there. And if we put on the dispersion forces, you can see who has London dispersion forces. But let's wait till this rotates around so you can see what I really want to see. Probably if I'd have put a couple fewer hexanes in it would be clearer. But you can play around with it. Okay. So you want to explain how those molecules interact in terms of their intermolecular forces, and then tell us what the significance of that is to life on Earth. That's it.